Hey guys, Miss McCorn here. Today we are going to be doing Unit 4, Topic 4.7, Types of Chemical Reactions. Today you'll be doing precipitation reactions, oxidation reduction reactions, better known as redox, and you will learn how to calculate oxidation number. So first we'll quickly look at precipitation reactions. This means the ionic forces are greater than the forces, intermolecular forces between the ions and the water. So they're not going to be soluble in water, but you're going to have an ionic compound form. This diagram here may give you a little bit of an idea. We have done this reaction in class where we have potassium iodide here, and we react it with lead nitrate, and we got this bright yellow liquid. I'm sure you guys remember that. And then at the end, after we let that reaction settle, we got this precipitate. And this precipitate here is this lead iodide. And the reason that happens is because the lead was more attracted to the iodine than it was to the water. So we have lead iodide forming here. So that is going to form an ionic bond, which is where you get that reaction. So the nitrate is going to float around in the solution, and these lead iodides are going to form down here, which is what you get sinking to the bottom. One of the very good things I found as I was going through this topic was that for this class and for the AP chemistry exam, the only solubility rules that you need to know are that these compounds here, sodium, potassium, ammonium, and nitrate, are all soluble in water. So anytime that you see these particular, any of these combined with something else, any salts like this, they are soluble in water, and these will be spectator ions. So these are going to end up crossing out in any of your balance equations and your ionic equations. So if your task is to predict the precipitate that forms when two solutions are mixed, the solid in that compound, it is never going to be anything with sodium, potassium, ammonium, or nitrate, because these are always going to be your spectator ions, and these will always be soluble in water. So an example of a precipitate reaction is listed right here. Write the balanced complete ionic and net ionic equations for the reaction that takes place when aqueous solutions of lead 2 nitrate and sodium iodide are mixed in a beaker. So you need to write out the equation, lead 2 nitrate and sodium iodide. So what we did, we just saw that was our beautiful yellow reaction. So to see that, okay, you see the lead 2 nitrate and the sodium iodide, and then you're going to want to balance that. What we know is that anything with a nitrate is going to be soluble in water. So your nitrates are always going to cross out. They're going to be spectator ions. We also know that our sodiums will always be spectator ions, and those are always going to be crossed out. So what we're left with is our lead plus our iodine, and those are going to be our ions, and we will have our lead iodide here as our solid. Okay, so that is our net ionic equation. So when this reaction occurs, the lead collides with the iodine, and they are going to be more attracted to each other than they are to the water. Here's your checkpoint question. Go ahead and answer this using the quiz question that pops up for you. So oxidation reduction reactions, we very, very briefly talked about this last semester. This is often referred to as redox reactions, electron transfer reactions. So one substance is going to lose electrons, and that's called oxidation. The other substance is going to reduce, and that is when it gains electrons. It does sound funny that something that loses electrons is oxidized, and when it gains electrons, it's going to be reduced, but we're going to look further into that. Here's a single replacement example. A piece of iron is immersed in a solution of copper 2 sulfate. So you write out the ionic equation here, and what we see, this again is a net ionic equation, and this is the oxidation reduction reaction. So you might find it strange that we refer to the substance that gains electrons again as being reduced. But what we're going to see is that this is actually talking about the oxidation number. And now I'm going to show you actually how to calculate the oxidation number. So how can you tell what gets oxidized and what gets reduced? So what I like to look at is that if I was to draw the Lewis structure of calcium, you know I would have, I can't draw with this pen. Oh my goodness gracious, one moment please, while I erase that. Okay, if I were to draw, really, it doesn't just happen in class, guys, this also happens on video. So if I were to draw the Lewis, holy goodness, the Lewis dot structure for this reaction, I would actually draw 2 dots here for calcium to represent the electrons. And of course we know oxygen would have 6 on each of its 2. So we'd have 2 oxygens, of course, with 6 different electrons there. So what I would like to see is that one of these electrons is going to be transferred over here to the oxygen, right? Okay, and when that happens, we know that oxygen is going to become negative and it's going to gain some electrons when it comes onto this side. So that one, the oxygen atom is gaining electrons and we call that reduced. Okay, oxygen gains and we call that reduction. I have no idea where these little things right here come from. I really apologize for those. So let's look at another example as to and explain these oxidation numbers I'm talking about. I'm going to go rather quickly through these oxidation rules, the rules for oxidation numbers. So what I want you to do is pause the video as you need to, jot these rules down. I'm not going to read each slide for you. I'm just going to go rather quickly through them so you can see each of the rules and get some checkpoint questions along the way. They are pretty self-explanatory. When they do need explanation, I will give you explanation for them. Here is the oxidation number for a monoatomic ion. The oxidation rules for oxygen. There are 2 oxygen atoms in CO2, so the oxidation number of oxygen, -2, you have to actually multiply it by 2, as you see here, okay? The only exception are any peroxides, okay? And when you have that, your O2, anytime you have a peroxide like that, the oxidation number is going to be -1. That is just, you guys know, chemistry, there are always going to be exceptions. Okay, here are the oxidation rules for hydrogen. Oxidation rules for covalent compounds. Oxidation rules for all the atoms in a compound must always equal the overall charge of that compound. So of course we know water is neutral, so it has to be 0. Here we have another example. The sum of the oxidation numbers for all of the atoms in the compound here have to be -1. So we already know that oxygen is -2, multiplied by 3 is -6. That has to make the chlorine has to be a +5. Okay, so here is a checkpoint question. Go ahead and answer that. Here's the explanation for that. Since chlorine is the most electronegative based on the covalent compound rules, the oxidation number of it has to be -1. That means that since there are 5 chlorines, they have to be -5. The overall has to be a 0, so that means that the phosphorus has to be a +5. So to find out what gets oxidized and what gets reduced, you have to find out what is the oxidation number of each one of these. So the oxidation number of calcium is 0. Oxygen is 0 on the elemental side. So we know that oxygen on the elemental side is 0. And calcium, and anything in their elemental form, is always going to be 0. So we have to look at this compound. We know that oxygen is always -2, and calcium is going to be +2 to offset that. So because oxygen gains electrons, it is going to be the one that is being reduced. Therefore, calcium is being. Take a second and take a look at this one. Pause the video for a checkpoint just on your own. So here is the answer just to check yourself. Now you can go ahead and complete the rest of the checkpoint questions that'll pop up